right, so we just finished talking about ionic bonds. So we talked about these. Now we need to talk about covalent bonds. Now remember what I said about the shells. They're called valence shells. So when we talk about covalent, co means with. Covalent bonds happen when you have sharing of the valence electrons, okay? So covalent bonding is when atoms share one or more pairs of electrons. Molecules are when you have pairing of atoms, when you've got atoms kind of stuck together. Electrons occupy shells outside of the atom's nucleus. We know this. First shell rule is 2. Second and third shell is the octet rule, so it's 8. So we can have sharing of pairs. One pair would be a single covalent bond. 2 would be double, triple. You can even have up to quadruple in our class. So let's talk about that. Let's go to hydrogen. Hydrogen is at position 1 up here in the upper left-hand corner. So if we were to draw this, knowing that hydrogen is at number 1, right? That means we have 1 proton, we have 1 neutron, and we have 1 electron, right? So if we draw that, we've got 1 proton, we have 1 neutron, and in the first shell we have 1 electron. Am I happy? Do I follow the rules? No. What's the rule for the first shell to be stable? 2 electrons, right? So, looking at hydrogen, how many do I need? I just need 1, and then I would have 2 in that shell, correct? Well, who else only needs 1 electron? The obvious answer would be another hydrogen. So if there's another hydrogen around that has 1 proton, 1 neutron, and 1 electron, technically they can share. Okay? Now, why do I mention this? Because if they're sharing, that means this guy sometimes comes over here and this guy sometimes goes over there. It's almost like having an infinity symbol around these 2 atoms, because these electrons are sometimes going over to the neighbor, sometimes staying where they originally are. But ultimately, what happens is you have, for this atom, 1, 2 electrons, and for this atom you have 1, 2 electrons. Now, it's not that they have them forever. They're not taking them away. They're sharing. That's why it's called a covalent bond. We're sharing with somebody. Now, in this case, this is called a single nonpolar, I'll explain that in a second, covalent bond. Okay, I've got 1 pair that I am sharing, nonpolar, like I said, I'll explain in a minute, and it's covalent because we're sharing. Now, going back, let's look at oxygen. Oxygen is here in the upper right-hand corner, and it's at number 8. So, oxygen is it number 8, right? So in a perfect world, that would mean 8 protons, 8 neutrons, and, whoops, that wasn't the button I was looking for, 8 electrons. Again, perfect world, right? So let's draw that. 1, 2, 3, 4, 5, 6, 7, 8 protons. 1, 2, 3, 4, 5, 6, 7, 8 neutrons. First shell, what's the rule? 2. 1, 2. Is that 8? No. 3, 4, 5, 6, 7, 8. Is this oxygen molecule happy? Or is this oxygen atom happy? No, it is not. Why? Because the second shell isn't holding 8. That octet rule still applies. So, to make this a little easier, who else needs 2? Well, another oxygen would need 2, right? So, let's draw another oxygen molecule. 1, 2, 3, 4, 5, 6, 7, 8 protons. 1, 2, 3, 4, 5, 6, 7, 8 neutrons. First shell, 2 electrons, 1, 2. Second shell, 6 to make a grand total of 8. So 1, 2, 3, 4, 5, 6, 7, 8. Now, if I share that pair and I share this pair, technically I'm happy because I have 1, 2, 3, 4, 5, 6, 7, 8. Again, that infinity symbol, I'm not always going to have them, but I have them long enough to make me stable. Now, the other oxygen, the one on the other side, am I happy? Well, I've got 1, 2, 3, 4, 5, 6, and with my sharing, 7, 8. So I'm happy too. Okay? So you've got, in this case, a double nonpolar covalent bond. Now, double. Why double? Because I'm sharing 2 pairs. Why covalent? Because I'm sharing. Covalent means I'm sharing valence electrons with somebody else. So, you've got 2 examples here. Now, you can have triple nonpolar covalent bonds. You can even have quadruple nonpolar covalent bonds. I'm just not going to draw them. So, let's talk about when it's a little bit different. What is the chemical formula for water? H2O, right? What does that mean? I have 2 hydrogens and I have 1 oxygen. So let's draw that. Protons. For oxygen, it was 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Again, perfect world. Neutrons. 1, 2, 3, 4, 5, 6, 7, 8. Our shells with electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now, let's draw our hydrogens. Each one has 1 proton. Each hydrogen, because I've got 2 of them. Each one has 1 neutron. And again, perfect world. Each one has 1 electron. Is anybody happy in this scenario? Because I'm not sharing yet. No, everybody's really mad right now and explosive. So what can I do? Well, I can share. I can share here. Now, if I just do that, this guy is ecstatic. I have 1, 2 electrons in my first shell. I'm good. This guy, however, is not, because I have 7. I don't have 8. And this guy is also not happy because I have 1, not 2. So what do? Well, I share again, except I share over here. Now, this guy has 1, 2, 3, 4, 5, 6, 7, 8 in his outer shell, which makes him happy, right? That was terrible, sorry. This guy has 2, 1, 2. This guy has 2, 1, 2. So everybody's happy. Now, this is where things get interesting. So, go with me on my journey of a story. I have 3 older brothers, okay? The one that's oldest is 10 years older than me. Now, if I was playing with a toy and my older brothers wanted the toy, what do you think happened? Yeah, they got the toy. Why? Why did they get the toy? And it's not because they're bigger. It's because they're stronger, right? They're stronger than I am. So they were able to take the toy. So they took the toy. What's the first thing I did? So what happened? Mom came in and went, whah! Give her the toy. And I got the toy. Right? Well, then what happened later? Once mom left. Yeah, they could still take the toy. Why? Because they're stronger than I am, right? So think about this for a second. Who is pulling on the electrons? What is the opposite charge of an electron? An electron is negative, so who's pulling? The protons are, right? Because the protons are positive. Yes? How many protons do I have up here with my oxygen? I have 8 protons up here, right? And down here, I only have 1, right? So imagine this as big brother, who's stronger, and this as little sister and little sister. Okay, so when it comes to the pull on those electrons, it's stronger in this direction. Okay, so we're going to pretend that oxygen can take all of the electrons. It can't, but we're going to pretend that it can. If it did that, if it took all of the electrons up into itself, I would have 8 protons up here. And then if you counted all the electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I would have 10 electrons, right? If you do the math on that, that would mean that it is negative up at the oxygen, right? Now again, this doesn't really happen, but just go with me on that journey, right? Yes? So if I actually did take that electron completely away, what's left down here that has charge at this hydrogen? Just that proton, right? So that would mean that down here, I would have a positive. Again, that's not really how it works. I don't want you to think that that's actually how things happen, because it's not. But if it did, okay, if it did happen that way, that would be an explanation as to why it would be more negative near the oxygen than it is near the hydrogens. Now, remember what I said about me doing the, right? What happened when I did that? My mom came in and went, "Whas, give it to her," right? Well, you can kind of think of Mother Nature as my mom, because Mother Nature will not let oxygen completely take these away. Yes, oxygen does kind of have them for a little bit longer of a time frame, but oxygen still has to share. So I'm going to show you a couple of things and you tell me what they mean. What does that symbol mean? Money. What does this symbol mean? At. This is just another symbol, okay? And it means partial, meaning sometimes. When it comes to water, the oxygen is partially negative. We just explained that with the stinginess with the electrons, right? Which means that our hydrogens are partial positive. So within the same molecule, you have this unequal sharing of the electrons, and that causes this difference in charge within the same molecule, okay? So water is actually considered a polar covalent bond. Polar because there is unequal sharing between the partners. Back here, I said that this was nonpolar, and I said this was nonpolar, right? The reason that they're nonpolar is because nobody is stronger than the other. I've got one proton over here and one proton over here. Nobody is stronger than anybody else, so the pull on those electrons is completely equal. I've got 8 protons here and 8 protons here. Nobody is stronger than the other, so the sharing is equal. So here, because of that difference in proton number between the oxygen and the hydrogens, it is unequal sharing. Are they still sharing? Yes, they are, but it is not equal. So when we talk about covalent bonds, they can either be polar or they can be nonpolar. If they are polar, it is unequal sharing of electrons because the different numbers of protons. So if you were to draw an electron cloud around water, see the dotted line here? That dotted line would be complete equal sharing. But when you look, do you see that shift this direction with this yellow? That's actually that unequal sharing. Oxygen holds on to those electrons a little bit more than the hydrogens do. Do they completely take it away? No, Mother Nature wouldn't allow that. But it does create a partial charge. Nonpolar, that term is equal sharing of electrons. Why? Because the atoms have the same number of protons on both sides.